Yeah, dude, yeah.
Okay. Any questions before I go into material from this section? Any questions? Okay. So here. Okay. There was an error in the Canvas. I had a typo in one of the questions that we had as far as the answer. So it was like supposed to be like S+3 and it was like S+2. I just mistyped it. So all of those answers are wrong for everybody on that. So it's going to take her even longer to grade because she has to go back in and grade those. So I'm going to shout out to Ian Martin, who looked at that and was like, this is not matching up with your solution. So Ian actually found that. So thank you, Ian. All right, any questions though about the exam? Is if you've already gone over it and had questions about the general solution for it? Yes. Okay. Okay, any other questions, comments about the exam? Okay, feel free to reach out to me. My email during this time is really high, so just note that. I need to put on there, like, please note that I have high volume right now. Just with registration, I tend to get a lot of extra questions. I had 1,000 emails the other day, so just be patient if you do send me an email. I've been trying to be really on top of it, but it's a lot of emails to go through. So, not that I'm ignoring you. If you don't hear back from me and it's been a couple days, do ping me to get it back to the top of the list of like, have you thought about this or could you give me a response? Feel free to ask questions about coursework in here too. All right, going back to the material in this unit. So I think my head around like, how can I explain this in a little bit better way? So last time we started talking about power with time dependence to it. So now we have a power unit that has voltage as time and current as time. And so this varies over time. And so sometimes it will be 0, sometimes it will be high value, sometimes it will be low. So unless we're talking about one specific time, it's hard to understand kind of what is going on with the time dependence power. So with some things, we usually describe them like, oh, well, we can average over something. That gives us more information about a quantity. What happens when we do an average over a cosine though? It's 0, right? Because it goes up and down equally. So that's not going to be a descriptive means of expressing what this quantity is. So that's where this term root mean square comes in. And that is, so this becomes a 0. It is considered the standard value to use that explains the effective value because that 0 is the average. And so this is a little bit different where you actually are square rooting the square of the term. And so this is kind of our standard value that gives us a number to understand kind of what is going on over time. So it gives you over one period of time what is kind of going on. So that's something we can interpret. So that's kind of hopefully a little bit better description. Does that make sense?
Yes.
Yes. Okay.
So if we're plugging, if x of t was the cosine, the average would be 0, but the RMS would be.
Correct. Yep. And another way that you can think of this is that, down here. No, I didn't put it there. Where's the other one? Okay, another way to think of this is it's a definition to find the AC value, which relates it to a DC value, which is what we usually know of like in a circuit. So usually like with the DC value, I showed you the example where if it's DC, it gives you like 20 watts or 10 watts. I can't remember what that example was. But if it's an AC, it was hard to understand what was going on because it goes up and it goes down. But this effective value gave us the same as if it was a DC value. And that's where the RMS comes in. So it actually relates it to exactly what you would think it would be as an average value in DC. I'm going to just copy this. Okay, the other thing that was a question last time is I used some numbers that actually came out to be like 1 over the square root of 2, and somebody was like, well, where did that come from? And I said, well, that's just the VRMS of that. And so I wanted to go over that quickly as far as that number and where it came from. In these notes, I've kind of created this equation set. So in this one, and then going forward, there'll be this equation set, which is useful to have. And then we'll kind of keep talking about like, how do you use these numbers? So quickly going over that, the average was of any kind of signal. I'm using X to signify any value. So it could be voltage, it could be power, it could be current. Any of those is going to be the average, which is integrating over that time period for one period. Over one time period. Average, oh my goodness. Anyway, that's the average. And then the root mean square is the square root of the square of the signal. Average power is going to be the amplitude of voltage and current over 2. And then cosine of the difference between shifts in the voltage versus the shift in the current. Complex power is in rectangular form. The complex power in rectangular form gives us this P value, which is the real power. Remember, that's going to be in watts. The Q one is the imaginary or reactive power. And that is also a watts, but to differentiate these, we have two new terms. VA for this complex power, S. And what VA is going to be, or what the magnitude of S in the polar form is going to be the apparent power. So these are just terms to understand. And then that one is in volt ampere. It's still a watts, power is watts, but it means that it's volts ampere, meaning an apparent power, but that also denotes that it's complex. So when you see volt ampere, you know that it's a complex power that it's talking about. VAR is going to be volt ampere reactive, meaning just the imaginary part of the complex power. Okay, so they're all watts, but now we have 2 new terms to differentiate in the complex plane. So complex power, VA, complex reactive portion is the Q, and that's VAR. We then also have this power factor, which is the average power over the apparent power. And then you have to know the relationship between the shift in angles. So that was where this theta, which is the shift from the voltage subtracting off the shift in the current, that difference tells you if you're leading or lagging. And then the PF gives you a number. So you have, for the power factor, 2 quantities that you're trying to find. The number itself, and then the shift between the current and the voltage to tell you is one leading, is it leading or lagging? Or just purely resistance only. And that will be a PF of 1. All right, questions about these terms? Okay. All right, so now we're going to go over that. Okay, so if V of t is just Vm cosine. Cover this for a minute. Okay, so this would be. Sorry, I'm gonna erase some of this. Okay. All right, so this is the equation for the root mean square. So the square root of, I'm gonna keep that. The V of t squared dt. And so that just puts cosine squared over one time period. And the period, which is not relevant here, is usually 2 pi over omega. But that's just kind of a side note, so don't need to worry about that part. So Vm is a constant, so I can just take that one out front. So this becomes Vm squared over t, 0 to t, cosine squared omega t plus theta dt. So cosine squared of omega t plus theta v is actually has a property to it. So it's a half times 1 plus cosine 2 omega t plus 2 theta v. So I can just plug that in here. Maybe not. Okay, I'll not do that. So I still end up with square root over everything. And then this now turns into 1/2 plus 1/2 cosine. And then the 2 is brought inside due to the property. And again, I have a constant here. So I can bring the constant out. And what happens to this? As I integrate it, that term goes to 0 again, right? Because it's a cosine again. So this then leaves Vm squared 2t. And now just dt here. And then this term here went to 0. And so Vm squared dt, and then integrating with just dt gives me a t, and I evaluate it from 0 to t. And so Vm squared dt times, this is t minus 0. So then the t's cancel, and I get Vm, if I want to bring it out of the square root, over the square root of 2. So if it's not Vm, if it's just even a generic xm, this is going to be the same quantity. It's going to be, as long as I'm in the form of an amplitude times a cosine, and it can be a cosine with a shift or just a cosine. It's going to end up being the same for both. The value ends up being that amplitude over the square root of 2. And so this is where that came from, is that VRMS is equal to the amplitude of Vm over the square root of 2. So we're going to use this a lot. And this makes it also easy. So whenever I have a cosine and I want the VRMS, which is really that way of describing that standard average, it's just a little different, is to take 0.707 of that amplitude. So 1 over the square root of 2 is 0.707. So it's about 70% of the height and the amplitude in the positive side.
This is kind of unrelated, but this really only works like over a period, right?
Mhm.
Is the same approach you use, like, if trying to calculate if you're not over or period, like not over something.
Mhm.
Good.
Yeah, so we kind of use this as the standard way. We assume everything is described as cosines. And so you learn that kind of in 1240 is like, you can't actually rewrite any signal with a whole bunch of sums of cosines. And so you can make an estimate value of like, okay, I have some chaotic signal and I kind of see like the height of that at some point and take this 1 over the square root of 2.707 of that. And that gives you that effective value to use. And so, yes, you could use that to create kind of an assumption to work with of any signal at all. Does that help? Okay. All right, any questions about this? Okay, you guys ready to work on some more problems? Okay, so this is just review from last time, and then we were working on this problem. We worked on A. And so go ahead and now work on B. Yes.
Again, sorry.
Yeah, no worries. Let me draw the cosine. Okay, so for one period of a cosine, it looks like this. And what the integration does is you're taking actually the area underneath the curve. And so in this case, they add up to 0. Does that answer your question? I mean, you can integrate it, but it will end up being 0. It's easier visually to see it. Like, oh yeah, thought it was going to be 0. Yes. Yep. Yes.
Does that mean that we have to integrate over a full period?
For the cosine, you mean?
Yeah.
Yeah, so that's this description of average, and the root mean square is over one period.
Okay.
And so you're always taking it over that one time period.
So what we have to do is up the period of time, and just put it in, or, well,
Yep.
Okay.
So, yep, you don't even have to.
My name, ARMS, and then my. So today's be. In this case, it'll be 12. And then it's a couple of time shifts.
You get that. Oh, yeah. You did the same thing like oh, I'm saying
Oh, yeah. My arms. Power. We are.
One over this. Yeah. That one. Oh, I think it was. Which. Let's do this. Did you just look at you want as soon as you want?
And then you have to.
I feel like it's 80, 180, minus J. Took the magnitude of it from P, I would think. It's the real. Yeah, because P average is the real. Yeah.
I feel like
Conflict.
the real part of it.
That is complex. So
So the being we are meant.
Okay, so it's.
this is the conflict.
Yeah, because I was moving.
Oh, this is their average.
Putting the F into that.
This is where P average. This is the conflict.
So you.
P and average. 6, 3, 5. And then I can just say.
It doesn't do a magnitude.
So that is the rest of the it's just the S.
This that reduce it down. But realistically, like, oh, I did.
Yeah, I guess. So yeah.
That's what I understand.
That's in values.
I can react.
This one is like why? That could be for the.
Reactive power. Now we need to find power back. Power is Parent power is this. The average. This is average. Is the magnitude of that? Right, so 6 would be divide that by 220. So I got. Oh, we have to figure out what it's, if it's leading or not. Now we gotta figure out if it's leading or not, this value, and I don't understand with this. Oh, they're literally stating like voltage. Yeah.
Mhm.
So whenever we see less than eight, it's always rows that have. Okay. So. Back. So is that like?
So
Well, it's like about the same.
Mhm. Yep. That will be in
Because
us.
it's just both of them.
It's watts over watts.
Oh, yeah, it's lots of them.
Well, but yeah, watts with distinguished or specific watts, so, but they, yeah, they basically. Every power. All right, so here are the answers. So do check that you were able to get the same answers. So to start this, you want to write VRMS and IRMS in the phasor form because you're given them in the cosine form. So you change them over to phasors. And then you take VRMS times IRMS complex conjugate. So remember, the complex conjugate means you take whatever J, you change it over to a minus J. So in this case, it's minus 15 degrees. So that changes over to a plus 15 degrees. So your polar form for the complex power is 2.4 EJ to the 45 degrees. And that's in volt ampere. And then the apparent power is going to be the magnitude of that. So in this case, 2.4, again in volt ampere. And then you change it over to rectangular to get average power and reactive power. So I take that 2.4 cosine 45 degrees gives me the average power in watts. And then 2.4 sine of 45 degrees gives me 1.7 as the reactive power Q in volt ampere reactive, VAR. And then the power factor, remember you have two components of it. One is the number itself, which is going to be the average, in this case 1.7, over the apparent power, which is the magnitude in the complex or in the polar form, 2.4. And that gives me 0.8. And then you take the angle of V minus the angle of I. So that gives you 30 minus a minus 15, which gives you plus 45 degrees. So because that's a plus, that's going to be lagging. All right, questions on this?
does 45 degrees is positive. Line.
Yep. So yep. Positive means it's lagging. If it's exactly equal to 90, it's still lagging. If it's negative and even negative 90, it's leading. So negative means it's leading. So current in relation to voltage is what you're looking at. So leading or lagging between those two. That's what it means. Okay. All right. Questions about these terms? Questions about how to find these values? Okay. I'm going to post the rest of these answers. Okay, so as an exercise, I'm gonna let you guys, you can go through more of these solutions if you want to use them. I'll just post them kind of in the notes. So these will be the answers to C, D, E, and F. Okay, so next concept that we're going to talk about is called this maximum power transfer. Do you guys remember the maximum power transfer for a DC circuit? Yes, no? Kind of remember? You remember talking about it? Okay. So in the DC, when we talked about it before, we looked at power, and that was just in a DC value for VL and then times IL. And so we got IL squared, our load. So this was the voltage across the load, VL, and the current across the load, IL. So IL was defined as this VS, which is a more complicated circuit that you lump up into a Thevenin. So this VTH is equal to VS, and the RTH represents RS. So just think about that. That was a really complicated circuit. Reduce it down to those two components, and then you put on RL. We wanted to know at that point what value it was RL going to be to create this maximum power transfer. So with that, this ends up being RS plus RL, and then the power gave me VS squared, RL squared over RS plus RL squared. So then we took the derivative of this with respect to RL to be 0, which gives you the maximum. And when you do that, this is the derivative here, and you set it equal to 0. Then you end up, the VS squared can be multiplied over to 0, and then I'm ending with 1 minus 2RL. No, that's not quite right. Let me do it this way. RS, let me get the same denominator. So to get cubed, this is going to be RS plus RL on the top. And then minus 2RL equals 0. And then this can go over to the other side and cancel. And this gives me the RS minus RL equals 0. And so RL equals RS. So this was what we found with the maximum power transfer, was when our resistance of what that RTH was, if we put the load to be that same R, it gave us the maximum power transfer we could have. So in the terms of now complex, we can do the same exact thing. So in complex, we have now that Z instead of R, but we treat it just like a impedance. And so VL is going to be IL times Z, IL times Z, which is R plus XJ. And the voltage is going to be I times Z. And then IL in this case is just VS over the addition of both of those terms. So an RS plus XSJ. I'm just going to write X. Well, I guess I can denote it as. And then RL plus XLJ. Oops. XLJ. And so just plugging these in, we can then get the complex conjugate of I. Now this is going to get messy to explain. Doing this, it ends up giving us I RMS squared R plus XJ. And now let me go back. Okay, sorry. Going back to this. Oh, okay, here it is. Okay, so this is, let me keep going this one. So this is going to be your P average, L, complex conjugate. And then all we're going to do is take this power average with respect to RL equals 0. And doing like we just did, we're setting this equal to 0. These are going to cancel. And we already have, bottom will also cancel. So we have RS plus RL squared. XS plus XL squared minus 2RL RS plus RL. And that equals 0. And then solving this for XL is what we're looking for. Let's see. I'm missing something here. RL. XS. So in order for these terms to go to 0, this term let me do a side note. Okay. So taking the partial derivative with respect to XL gives me, oh, it's this one. Okay. So this is the partial with respect to RL. And this is the partial with respect to XL. And so this is going to go to 0, or this can be divided over to the other side, and this can go over to the other side. And so you get from this, you get XS so XS equals minus XL. And so when I plug that in here, that gives me that this term goes to 0. And then RS plus RL squared minus 2RL RS plus RL equals 0. And I can solve this, and this gives me that RL will equal RS. So what this means is that the maximum transfer happens when RL equals RS. So that's very similar to what we had before, right? When we looked at just real values, RL equaled RS. That stays the same. The difference is now that the time-dependent elements, they have to be opposite, so a negative of each other. And then that gives us maximum power transfer. So excess is what's in the actual circuit. And so to match that, we just have to take a negative value of that. So if it's an inductor, we have to put a capacitor. If it's a capacitor, we have to put an inductor, basically. So they're gonna match that impedance. So this is then the maximum power transfer is that ZL is just equal to the complex conjugate of ZS. And that's all we have to do the maximum power transfer. The average maximum is 1/8 VS squared over RL. So that is the voltage in the source, or the Thevenin equivalent voltage, squared over RL. All right, so here is a problem. It says to choose the load impedance. And so to do this, we have to first find the complex Thevenin equivalent of it. So that's going to be your first step, is a complex Thevenin. Then you're going to just match ZL with the complex conjugate of ZTH. And then you're going to find the average power max by 1/8 VTH squared over RTH. So to find this, as you can see, this is already transferred into the phasor domain. So you're going to want to change the components, everything again, into phasors. And to find VTH, all you do is put where you're trying to find the load as A and B, and that will be your location of VTH. So in this case, we want to find it between these two nodes as VTH. So with that, I'm going to put a ground here. And you guys all know that I love node voltage. So I'm going to label this middle node as V2. I'm going to label this one as V1. And the node at A is actually an ordinary node. So I don't need to actually write a different node voltage there. Once I find V1 and V2, how do I find VTH? So say I do my node voltage and I solve this and find V1 and V2. How do I find the VTH from that one?
Find the current into it and then multiply it up to 4.
Okay.
Or yeah, you then use Ohm's law with 4.
Okay, so if I found I here, then VTH will be what? So if I write V1 goes from ground to that node, right? And VTH is already kind of labeled here. It goes from this node to ground. And then if I label my I in that direction, I have a plus and minus. So if I do a loop around here from ground back to ground, I would do a plus here, minus and minus. So plus V1 minus I times 4 minus VTH. That's how I like to find those, is go ground back to ground. But you need to know what polarity each one is. So I like to label the polarities and then circle the signs to be consistent. I could have chosen the negative sign first, so then I would have circled negative for V1, plus for I 4 ohm, and then a plus for VTH, but it would yield the same thing. So now I have an equation. I can just solve this for VTH. So that's going to be V1 minus I times 4. And once I know V1, I can solve that one. How do I write I in terms of V1 and V2? Go for it, you sure.
The top I or like I, V2 I?
And the I going through 4 ohm. Oh, sorry. I had 2 Y's, didn't I? Okay, I'll call this IX. Okay, this will be my IX. Sorry, I didn't realize I had another I in there. So how do I write IX here? So when I have a current, I take the opposite where the arrow is. So I start there. What's the voltage there? V1. And I subtract off any other elements or any other voltages in that loop. So in this case, the element value is 2I. So dependent sources you treat just like you would a voltage source. If they're plus and minus in them, that means it's a voltage source. If they're current source, you treat it just like all the current is known in that branch. And even though it has a variable as the value. So in this case, that value is 2I. But if we knew I, it would be, say I was 10, it would be 20. So you treat I like, I mean, it is a variable still, but it's some value. So minus 2I. And then minus V2 would be the other voltage. And then what is that over? Yep. So that would be my description for IX. And then I noticed that I is now in this equation. So I have to write an equation for I. What will be the equation for I?
V2 over V1.
Yep. So there's my I. So now I have I, IX, VTH, all in terms of V1 and V2. So I can write now my node voltage equations for V1 and V2. So let me start with V1. So what will I describe this current as? The one going through the 1 ohm.
V1,
So this branch right there.
V1 minus V.
Yeah, 8 EJ to the 0, but that's 1. So I'm just going to leave it as 8
Over 1.
over 1. And then going through the J2, what's that going to be?
V1 over, or V1 minus V2 over V2.
Correct. And then my IX, I already wrote, right? So I can just rewrite that one. So V1 minus 2I minus V2 all over 4 plus 6J. And then at the V2 node, okay, there's the I. We already wrote that one too, right? So V2 minus 0 over minus J. And then I can either do a minus of this one, which would be a minus V1 minus V2 over 2J, or I can write it as a new current going out, whichever 1. Some of you like, that is the ugly. Okay, so a minus V1 minus V2 over 2J, which ends up being V2 minus V1 over 2J. So whichever way you can write that, V2 minus V1 over 2J. So those are the same. And then again, this one's going to be a minus IX. Or I can rewrite that and that would be V2 minus a minus 2I minus V1 over 4 plus 6J. So either way, they're going to be the same exact term for that equation, and then that will equal 0. So I absolutely would not want to solve this one, so I'm going to use MATLAB. So I would set this up in matrix form and then plug it in. So I already did that. Copy. Oh. Okay, so setting that up and using MATLAB, I got this value. So I set up A based on these equation sets. So I used equation 1, equation, find a different color. Equation 2. And then I use the I and the IX and VTH. So this is my VTH. I2 I called IX. V1 minus V2 minus 2I1. Yeah. And then I was V2 over, note that you can rewrite this as V2J. So I just wrote that as V2J. And so this is my I, which is equation 3. And so I just put 1 and 2 into matrix. And then I used V's inverse of A times B. And that gave me a value for ZTH. Okay, this ended up giving me VTH was minus 2J. Do you guys want me to write these two equations in matrix form to see them? I'm saying yes. Okay, enough of you do want that one. Okay, so from here, I have terms V1 and V2. And then from equation 1, my V1 terms, I have 1 and then plus 1 over 2J. And then here is 1 over 4 plus 6J. And I did substitute in this V2 here, V2J. And then I use this one for V2J here too. So then my next term, I have 1 over 2J from this one. And then this one I have minus j over 4 plus 6j. And then this term is a minus 1 over 4 plus 6j. Oh, sorry. I have a 2j. Why do I have it? Oh, minus 2. I forgot to write the 2 there. So minus 2j over 4 plus 6j, and then a minus 1 over 4 plus 6j, and then a plus. Or no, there was a minus. Yep, there was another minus. Sorry. That was a minus 1 over 2j. Okay, so there's the second term, and then those are equal to 8 from this term. And then the second equation, I have a minus v1, so minus 1 over 2j. And then here I have a minus 1 over 4 plus 6j. And then the second term, I have a 1 over minus j, or I can just write that as j. So I wrote this term as j v2. And then this one is a plus 1 over 2j. And this term is 1 over 4 plus 6j. And then a minus minus becomes a plus 2j over 4 plus 6j. And then that is equal to 0. And so those were those two equations. Any questions about setting those matrix up? Okay. And then from here, this gave me a value of ZTH was equal to minus 2j. So what will your ZL be? 2j. That's it. Hey, questions about this? Yes. Uh-huh.
Can you solve function?
Uh-huh.
Can you use it with complex?
Pretty sure you can. I think you can. You'll have to try it out. But I'm pretty sure you can. You don't have to use MATLAB. You guys could use other solvers. I don't remember who was in here was saying they used one, but it doesn't do complex numbers. So just make sure it's one that does allow for complex numbers. Okay, so now that we have the ZTH, this also solved VTH. Did I not write down VTH? Oh, I'm sorry. This was VTH is minus 2j. Sorry. I'm backing up. So VTH here was minus 2j. Okay, so now we have VTH. We can find the average power. And then ZTH, I don't think I wrote down ZTH for this one, but ZTH would just be the complex conjugate opposite for ZL. Oh, here we go. Okay, ZTH ended up being so this is going into material where I'm not going to be requiring you to do Thevenin for dependent sources. So I'm going to skip that step of solving for that one. And that's what the second section of the MATLAB. And so this yielded 2.5 plus 0.75J. So assuming that this was the steps of getting, what will ZL be here? Correct. So that would be our load. And how do you make a 0.75 J? What element will that be? Correct. So that negative is what clues you into it's a capacitance. If it's plus, it'd be an inductor. So this would be a resistor, R equal to 2.5. And the capacitor is going to be some value. Oops. So minus 0.75 J is going to be 1 over C J omega. So then you could solve for the actual value of C, but you need to know omega in order to do that, which wasn't given in this. From just a phasor, you can't determine what that omega value was. But know that it's a capacitance. The average power is just 1/8 the magnitude of VTH over RL. So what will that be? 1/8. What is the magnitude of VTH in this case? Okay. So you'll, oh, sorry, there's a squared there. So 2 squared. And what is RL? Correct. It's the 2.5. So this, put this as RL, is the load portion of that complex impedance. So that will be the 2.5. And then that equals 0.2 watts. Is what this is. All right, questions about this? Okay. All right, so far we've gone over several concepts: complex power, the terms themselves. So make sure you understand what those terms mean, the equations, how to use those equations. So we have complex power in polar form, which gives us the apparent power, which is the magnitude of it. Then you change it over to rectangular form, that gives you average power, which is the real portion of that, and reactive power, which is the imaginary portion of that. We also have the power factor value. And next time I'll go over more of like, what does that mean as far as a value? And then you get information such as leading, lagging from that. And now you know also how to get components if you want to match a circuit to get maximum power transfer from them. And my notes have dependent sources, so I'm going to change my notes to not have dependent sources because we're going to focus more just on normal independent sources. So just review like finding Thevenin for independent sources. Okay. Any questions? All right. Oh, discussion. So this week is just discussion, and I don't think there was an assignment.
He's on. I have finding this.
Okay.
Like, why are we not consulting?
So the branch is from here back to this. So J2 isn't in that branch. So this branch, the V1 minus everything else till the V2.
So it just kind of voids.
So I could rewrite that to look like it would look, write it down here. Plus minus. This is V1, this is V2. I could rewrite this, right? That's the same as that one. And then I also then would have. This is 2J. 6J, I don't know what that one was.
Four.
4, okay, and this was 2I. Those are the same circuit. So this branch, it's easy to see V1 minus V2 over 2J.
Yeah.
This one is going to be V1 minus 2I minus V2 over these two combined, 4 plus 6J.
Okay, thanks.
So because this is the same branch, this is an open here. So it's like, you know, there's an open there, A.
So you're saying that V1 minus V2 over 2J is equivalent to the top quotient.